Lagrange multiplier theory is very useful approach when we have convex constraint set. Let's consider this inequality constraint problem. So we have objective function f, and we also have some constraint set which is defined by few different inequalities and equality. So we assume that f1 through h1 through hm are affine functions, and g1 through gr are convex functions. And we have constraint with hi. Here I is 1 through m, and we have to satisfy hix equal to 0, and we have to satisfy gjx less than or equal to 0 for all j1 through r. Okay, so which means because we assume that hix is a affine function and gjx is convex function, the constraint set defined by this is also a convex set. You can very easily check this property, convex set property. How to check? You just need to check alpha x1 plus or minus alpha x2 also satisfy these conditions when x1 and x2 belong to the constraint set. We just need to this one. Okay, and this is very easy because gjx is convex and hix is affine. One possible example is this. So let's consider probability vector defined for d-dimensional space. Then x1 plus up to xd must be equal to 1, and because this is a probability vector, xi must be equal greater than or equal to 0. That must be non-negative for all I index I must be 1 to d, because we consider d-dimensional probability vector. Then with this probability vector, we want to minimize convex objective function f. Then for this case, for this example, what is h? There is only single h function, h1x. h1x is x1 plus up to xd minus 1. So we have to satisfy h1x equal to 0, which means x1 plus x2 plus up to xd must be equal to 1. And we also have we have to also have gjx. This is equal to minus xj for all j belong to 1 through d. So here we have the different g function and only one single h function. And since h is a affine function and g also a affine function, but affine function is convex function, so g also a convex function. So they define a convex constraint set. Actually, it looks like this with a constraint function, affine function, and inequality with convex function. Okay. So with these constraint functions, we can consider a barrier method. The barrier method is very simple trick, and with barrier method we can forget the constraint problem. So because of constraint, we already studied how to deal with the constraint set. We first just simply learn gradient descent algorithm without considering any constraint, and then project the yt plus 1 to the constraint set x. Okay, and the problem here is the projection is not easy task sometimes, and actually many places. So some people introduce barrier function like this. So what is the barrier function means? For instance, if your constraint set gx is equal to x times x minus 1, and this must be less than or equal to 0, then which means the constraint set is the interval between 0 and 1. If you add some additional cost function to the original objective function like this, then when gx close to 0, this minus log minus gx value will go to infinity. And since we are trying to find the solution that minimizes the original objective function plus some additional cost function, when this term diverges to the infinity, we never go there. We don't need to search that kind of boundary area because this value is too high. So the barrier method, so basically this barrier function, basically shape looks like this in the 0 and 1 interval, so that your optimization process always located here. When you learn gradient descent or some other technique, with any initial point here, the process never escape between 0 and 1 area because of this barrier function. Okay, and also another important factor for barrier method is it is good to have very flat area inside the constraint set. We need make the barrier function have this flat area. Otherwise, the additional barrier function will perturb the original solution because this shape will affect the optimization process. So in the end, fx star is not equal to fx hat. Let's say x hat is arguing this. So the obtained solution from the barrier method and the real solution may be not matched. Okay, that is one bad side of barrier method. One good side of barrier method, we remove the constraint, so we don't need to do projection. Okay.